Hi folks, welcome to the second calculus review. This is really focusing on applications of integral and differential calculus. It's just a presentation that I made for some of my students in PEI Canada. It's not produced by the IB, it's not endorsed by the IB. It's not an exhaustive list of all the types, just some of the key concepts. If you want to make the most of the presentation, probably the best plan would be to print out the notes using the link below, work through the questions, and then use the presentation to check. If you have a different way of solving a problem, that's fantastic. Please do that. Don't try and change what you're doing at this point in the course. The graph of f at x equals e to the x sine x is shown with the given domain. There's a max at the point A and an inflection point at B. Okay, so we're talking about this point here and this point here. Find f prime at x. Okay, notice we've got sort of two parts to the function. There's the e to the x and there's the sine x. There's no plus between them. Actually, we're having multiplication between them, so that means we've got to use the product rule. So, derivative of the first, so derivative of e to the x is just e to the x, times the second part, which is sine x, plus the first part, which was just e to the x, times the derivative of the second part. Derivative of sine x would just be cos x. So don't miss those product rules. Hence, find the exact coordinates of the maximum A. Okay, so if we're looking for the exact coordinates of the max A, that means we're looking for a horizontal tangent. If you go back to the original graph, at A, at this max, we must have a horizontal tangent, which means that f prime at x is equal to 0. So let's set our f prime equal to 0. We'll say 0 equals e to the x sine x plus e to the x cos x. All right, we might want to factor here. We've got e to the x's in both terms. So the zero product rule says we might get solutions if we can solve this. E to the x equals 0. And we'll get solutions if we can solve this. Sine x plus cos x equals 0. This first part here, e to the x equals 0, there's no power you can raise e to in order to get 0. So it yields nothing at all. The next one, oh, that's got a sine and a cosine in it. What if we put them on opposite sides? Because we know something about sine and cosine. Sine over cosine is tangent. Let's divide both sides by cos x. That'll give us sine x over cos x on the left, okay, which is just tan x. And cos x, negative cos x divided by cos x is just negative 1. So you might think about your unit circle. Where do I first have a tangent of negative 1? I know I have a tangent of 1 at 45 degrees. But over here, at 135 degrees, I'm going to have a tangent of negative 1. 135 degrees in radians would be 3 pi over 4. Okay, so that must be the x-coordinate. That's the first time that we have a tan of negative 1. And notice here on our graph, this corresponds to the first time we have a horizontal tangent in the graph. Okay, read the question carefully. Find the coordinates of the maximum A. So this might be sort of a 5 or 6 marked question. You'll only get part marks if you write the x value only. If we want to find the coordinates, we need the y value as well. So we need to find the original function at 3 pi over 4. Okay, the original function was e to the x sine x. So this will be e to the 3 pi over 4 times sine of 3 pi over 4. The sine of 3 pi over 4 is positive. It's in the second quadrant. So we'd have e to the 3 pi over 4 here times root 2 over 2. Or you might write this as 1 over root 2. Either way is fine. So all I'm doing here is finding the corresponding y value that goes with that x of 3 pi over 4. Okay, so the coordinates then would be an x value of 3 pi over 4 and a y value of root 2 over 2 e to the 3 pi over 4. If this were a paper 2 question, I hope that you'd just use the max function on your calculator. Okay. So this could also be written as 1 over root 2 e to the 3 pi over 4. All right, find f double prime in simplified form. So we have f prime up here. I'm going to need to use product rule twice when I differentiate. So derivative of the first part times the second plus first part times derivative of second. Okay. Actually, it turns out that this first part of the function up here is the same as the original f. Now let's differentiate this part of the function. So derivative of the e to the x is still e to the x, okay, times cos x plus first times the derivative second part. So derivative of cos x is negative sine x. If I write all this out again, I'd have e to the x sine x plus e to the x cos x plus e to the x cos x minus e to the x sine x. Ooh, look at that. We have a positive e to the x sine x and a negative e to the x sine x. So those are going to be gone. And I can collect like terms. I've just got two of these e to the x cos x's. So in simplified form, we get 2 e to the x cos x. It's quite possible that this would be a show that type question. Show that it can be written as 2 e to the x cos x. Hence, show that a is a maximum. So using what you just found, namely the second derivative, show that a is a maximum. What we need to know for a to be a maximum is that we found already there's a horizontal tangent there. We need to show that it's also concave down. Because if we've got a horizontal tangent and concave down, there's no other possibility than a max. That's what the second derivative test says. Okay, so we know that that x value that we're interested in was 3 pi over 4. We found it right up here. So let's figure out what's going on with the second derivative, which controls concavity at 3 pi over 4. So I'm just plugging it in to my second derivative. I get 2 e to the 3 pi over 4 times the cos of 3 pi over 4. Okay, that's 2 e to the 3 pi over 4. Cos, 3 pi over 4 is right over here, 135 degrees. Negative x values in the unit circle. This must be a negative value for a cosine. And it's negative root 2 over 2. Okay, so when I work that out, I get negative root 2 e to the 3 pi over 4. What we've just shown here is that we get a negative result. Because e to the 3 pi over 4, even though it's not a pretty number, necessarily, is definitely positive. So the whole expression here is negative. We've shown that our result is negative. So since f double prime at 3 pi over 4 is negative, that means that f is concave down. At x equals 3 pi over 4. Okay. Which means we do indeed have this situation where the curve is concave down and we have a horizontal tangent. There's no other possibility than to have a maximum. A is a max. Find the x-coordinate of the point B. All right. So the point B was a point of inflection. They're asking, do you know what happens there with your derivatives? So if it's a point of inflection, that means concavity changes. And let's take a look at it again. Concavity does indeed change. It changes from being concave up to concave down. Which means over here on the left side, we should have f double prime that's positive. And over here on the right side, we should have f double prime that's negative. At the point of inflection B, f double prime should be 0. All right, so let's figure out where we have a second derivative that's 0. We know that our second derivative is 2 e to the x cos x equals 0. Again, we could split this apart using our zero product rule. 2e to the x equals 0. That's not going to give us anything. Cos x equals 0. Ooh, where does that occur for the first time? Cos x is 0 at 90 degrees, or pi over 2 radians. Now, we could go and test this and make sure that we actually do have changing signs on our second derivative. But they've told us that B is a point of inflection. So we don't need to do the testing because it's implicit in the question. Okay? But if we didn't know that, we'd have to, say, figure out what f prime at, say, 1 is, which is a little below pi over 2, and find what f prime at 2 is, and show that it goes from a positive value to a negative value. Therefore, this is a point of inflection. Again, that's given to us in this question because they told us right from the outset there's a point of inflection at B. All right, write the asymptotes of, I'll just have to move that little recorder. Plus 3 over x minus 1. All right, so this function is undefined where x equals 1. That's going to give us our vertical asymptote. At x equals 1. There's the equation of the line. Now, for our horizontal asymptotes, we look at what happens as our x values go to positive or negative infinity. So imagine that I put in, say, 100 trillion for x here. So I'd have 3 over 100 trillion minus 1. 3 over 100 trillion is a very, very small number. And if I made it 1,000,000 trillion, then it's going to be an even smaller number. And as I get closer and closer to positive infinity, it's going to be so small that it gets infinitely close to 0. So this part here goes to 0. Now we could do this more formally, but it goes pretty quickly if you just look at it informally, in parts. Okay, that goes to 0. What happens to the number 2 as x goes to infinity? In the words of Rick Moranis in Spaceballs, absolutely nothing. So, as our function goes to positive or negative infinity, this whole function goes to 2 plus 0, or just 2. That's going to be our horizontal asymptote. Describe the behavior of this function for large values of f. Large values of x. This is essentially the same as asking you about horizontal asymptotes. You have 3x squared minus x over 2x squared plus 1. And we're looking at the limit as x goes to, let's say we'll just look at positive infinity to start with. We have 3x squared minus x over 2x squared plus 1. The little trick here that you can do is to multiply both top and bottom by 1 over your highest power of x. So 1 over x squared, both on top and bottom. That'll give us the limit as x goes to infinity of 3 minus 1 over x all over 2 plus 1 over x squared. Okay, dealing with this, we say, okay, as x goes to infinity, 3 becomes 3. 1 over x becomes 1 over infinity, which is essentially 0. 2 becomes the number 2, plus 1 over infinity squared. Okay, well, whatever that means is a very small number, essentially 0. So we're going to get 3 over 2. So as x goes to infinity, f at x goes to 3 over 2. Meaning there's going to be a horizontal asymptote at y equals 3 over 2. Okay, now to be honest, what I would probably do with this is take a little shortcut. I'd say my highest power on top is 3x squared, or my highest term on top is 3x squared. My highest term on bottom is 2x squared. Okay, those divide out, they give me 3 over 2. Because our smaller powers, or our constants, really don't make that much of a difference when we're getting close to infinity. Say if I had a different function, g at x equals, I don't know, 4x cubed plus 2x all over 3x to the fourth minus 1. I'd just take a look at what's going on with my 4x cubed and my 3x to the fourth. Okay, really that's going to give me 4 over 3x. And as that goes to infinity, or x goes to infinity there, I'd end up with a horizontal asymptote at 0. Okay, so there are these little tricks that you can use. If that doesn't sit well with you, by all means, go the more formal route and do this. Okay, consider the functions. F at x equals x, and g at x equals x by x minus 3 by x minus 5. Write an expression for the shaded area. Okay, assume that these are going to be GDC questions. So first step might be actually put in these functions. First function is x, next one is x by x minus 3 by x minus 5. Looks like we're going from 0 to 10 for our x's. So let's do the same in our GDC. Y values are shown from negative 10 to positive 10. Oh, didn't like what I did. Oh, I forgot an x. There we go. So it's always nice to have a graph that looks somewhat similar to what's given. If you use similar window settings, you end up with some sort of visual confirmation of what you're doing. Here, they're going to intersect at an x value of 0. Okay? And really at the origin, 0, 0. Now, where are they going to intersect next for that shaded region? Let's find out. Second calc, intersect, first curve, second curve. Guess, looks like it's around 3-ish. And we get 2.59. Okay, so at the point 2.59, 2.59. If I want to find the area between them, I need an integral between 0 and 2.59 of the top curve, okay, that would have been my g at x, minus the bottom curve, which would be my f at x. Now, I can go ahead and do that in my GDC. There are a whole bunch of different ways that you could do it. You could find the integral of g at x from 0 to 2.59, and then subtract off the integral of f at x from 0 to 2.59. I kind of like to do it all at once so that there are no rounding errors. So I'm just going to turn these two things off. And I'm going to put in a new function, which is g at x. That was x by x minus 3, x minus 5, minus the function f at x, which was just x. Now I get a different looking curve, so that's kind of the downfall to this approach. But I know that it represents this. Okay. So I can find the integral of that red part between 0 and 2.59. And in my GDC, I'll just go second calc from 0 to 2.59. Gives me 11.9 units squared. Okay. Now we're going to repeat that for a slightly different setup. So I still have a point of intersection at 0, 0. Have one at 2.59, 2.59. And then I'm going to have another point of intersection. So luckily I didn't actually get rid of my graphs in the calculator. I can look at this again. Okay. So that's going to give me a third point of intersection at 5.41. Okay, we're going to have to do this in parts, or one way to do it is in parts. The first little bit is from 0 to 2.59, and it's got g at x on top. So it'll be g at x minus f at x with respect to x. Now the next part, this part over here, changes things up a little bit. We're going to have to add on the integral here from 2.59 to 5.41. But in this case, the line is on top. The f at x is on top. So I have to reflect that in my integral. If I do this piece by piece, I actually already found the part that's in black. It was 11.88, which I rounded to 11.9 in the last question. And now I can go ahead and put in my f at x minus g at x in my calculator. Okay, so I'll turn off all my other graphs. F at x was just x minus g at x, which was x by x minus 3 by x minus 5. Okay. So this is sort of the missing piece of the puzzle, the part that's in green on the notes here. I want the integral from 2.59 to 5.41. And I get 15.08. Okay. If I add those together, it'll be 26.96, which rounds to 27.0 units squared. Again, there are a lot of other ways that you could have approached this. You could have noticed that the graph, which was my y3 that came from this black part, is just a reflection in the x-axis of what we did for the green part. So you could have found the integral of the one that's in black from 2.59 to 5.41 and just made sure that you called it a positive amount so that you don't deal with negative areas here. Okay, so and alternately you could have done it with 4 separate integrals. You could have looked for the integral of g at x from 0 to 2.59, then from 2.59 to 5.41. Same thing for f at x, and decided what to add, what to subtract. Lots of different approaches. I kind of like this one because most of the calculation is done for you by the calculator. All right, given that f double prime of x is 2x minus 2, and f at x has a min at 3, negative 7, find the equation of f at x. Okay, well, we can't get to f at x right away. The best we can do is to get to the first derivative, f prime. Okay, so if I integrate or anti-differentiate f double prime, I'm going to have x squared minus 2x plus some constant. We don't know exactly what it is. Now there's a min at 3, negative 7. If you forget the c, you're really going to have a hard time getting many marks on a question like this. There's a min at 3, negative 7. So when x equals negative 3, what does that tell us about f prime? It's a min. That must mean we have a horizontal tangent, or f prime is 0. Okay. So f prime at x is 0 when I have a 3 in for x. So I'm just going to sub this in. 0 for f prime at x. Okay, right here. 3 for x gives me 3 squared minus 2 by 3 plus c. 0 equals 9 minus 6 plus c. Or c equals negative 3. Put it all together, and now we're a little closer. We know that f prime is x squared minus 2x minus 3. We can get closer still. Let's find what f is. So anti-differentiate or integrate again. Okay, that x squared turns into an x to the power of 3, which needs a 1/3 out front, minus the x turns into an x squared, so we just get x squared here, minus 3x, plus another constant of integration. So I've already used the letter c. I'm just going to choose to use the letter d here. It's up to you, makes no difference. Now we can sub in the point 3, negative 7. So we have a y value of negative 7 when we put in an x value of 3. And we do that so that we can find the actual value of the constant of integration. So negative 7 equals 1/3 times 3 cubed, that'll be 9, minus 3 squared, which is 9, minus 3 times 3, which is 9. Wow, this is working out pretty nicely. Plus d, okay, that gives us negative 7 equals negative 9 plus d, or d is 2. Make sure you answer the question that's being asked. Find the equation of f at x. So substitute in that value. We get f at x is 1/3 x cubed minus x squared minus 3x plus 2. Tangents and normals. All right. Just be careful here. When you ask for the equation of the normal, you need to differentiate here to find the slope of the tangent. But normals and tangents are perpendicular to each other. So normal is perpendicular to the tangent, which means their slopes are negative reciprocals of each other. Okay. And eventually we're going to need to sub this into our point slope formula to find some equation of the line. Okay. So what we need for the equation of a line is a point and the slope that we're going to use. We know here that we're going to use an x value of 1. And let's just make sure we find the corresponding y value. So that would be 1 minus 3 when we plug it in over here. 1 minus 3 is negative 2 times e to the power of 1. So negative 2e would be our corresponding y value. That's our point we'll have to use. To find the slope, we're going to have to first differentiate. Okay, so let's use product rule here. X minus 3 all times e to the x. So derivative of the first part, derivative of x minus 3 is just 1, times the second part, which is e to the x, plus x minus 3, first part, times derivative of e to the x, which is just e to the x. Let's put them together, see what we get. E to the x plus x e to the x minus 3 e to the x. We get y prime equals x e to the x minus 2 e to the x. And actually, this simplification probably wasn't all that necessary. At x equals 1, we get y prime of 1 times e to the 1, or just e, minus 2 times e to the 1, or just e. Okay, which is negative e. That's the slope of the tangent. If we want the slope of the normal, and I'm using the letter m here for slope, we'd have negative reciprocal of negative e. So flip it upside down, gives us 1 over e, and change the sign, gives us positive 1 over e. Now let's substitute in what we've got. Okay, so y minus y1, which is negative 2e, equals m, 1 over e, x minus x1, which is just 1, y plus 2e equals 1 over e, x minus 1 over e. Okay, it doesn't really specify what form we want to put this in. If we were going to use it later on with, say, our GDC, we'd probably want it in y equals form. So let's throw it in that form. Oh my gosh, and we are going to use our GDC in the next part. Find the coordinates where the normal cuts f at x again. Let's see. If I want to do this, I'm going to need to set the original curve and the normal that I just found equal to each other. Okay, so the original curve was x minus 3 times e to the x. Our normal was 1 over e times x minus 1 over e minus 2e. We know that they're going to cut each other at 1, negative 2e. We want to find the other coordinate. Okay, so let's go to the GDC. Get rid of all this other stuff. We have x minus 3 times e to the power of x all over 1 over e times x minus 1 over e minus 2e. Okay, I'm really not sure what these are going to look like, so I'm just going to go to my standard settings. Oh, there we go. So you can see right around here that we've got that point of intersection at negative, or at 1, negative 2e. Here's the other point of intersection we're looking for. Second calc, intersect, first curve, second curve. Let's guess, it looks like it's around 3-ish. And we get this point of intersection at 2.66, negative 4.82. So you might want to sketch what you've got and show that it cuts at 1, negative 2e, and also at 2.66, negative 4.82. We're sketching our method here. It doesn't need to be a thing of great beauty. And make it clear that that is your answer. Applications to kinematics. Okay, so if you've got displacement, which we're going to call s at t, but really it could be x at t, could be whatever you want in terms of the letters. If you differentiate displacement, you get velocity. Differentiate again, you get acceleration. or we can move in the other direction. If you've got acceleration, integrate, that gives you velocity. If you integrate again, you're looking at displacement. But be aware when you integrate, you've always got this plus c, this constant of integration. All right. The velocity function of a particle is given by v at t equals 3t squared minus e to the 2t plus 1 over t meters per second for t greater than 1 second. When t equals 3 seconds, the particle is 5 meters right of the origin. Find the displacement when t equals 4 seconds. All right, so we've got velocity. We want displacement. We need to integrate. So let's do it. S at t, our displacement function, is going to be the integral of this one, or the antiderivative. So we get t cubed minus half e to the 2t plus ln t plus some constant of integration. But we know something. When t equals 3 seconds, so s at 3, we're 5 meters right of the origin. So we're going to assume that means positive 5 in terms of our displacement. Okay, that gives us, let's sub them in, 5 for s at t, 3 to the power of 3 minus a half e to the 2 times 3, or e to the 6, plus ln 3 plus c. Okay, pretty straightforward equation for you to solve in your GDC. We won't take the time out to do it right now. You can take my word that it's 179, or you can send me an email saying that it's not. Okay, now that we know the actual equation for the displacement. E to the 2t plus ln t plus 179 at the end. Okay, so now all we need to do is sub in 4 for t. And if we do that in our GDC, we're going to get negative 1246. Or you could write it to 3 sig figs as negative 1250, ideally. Okay. Which we're going to interpret to mean 1250 meters left of the origin. So we integrated here, we made sure we found the value of the constant of integration, then we used this displacement formula, or this displacement equation, to figure out our actual displacement at 4 seconds. Find the acceleration when t equals 4 seconds. So we knew that v at t was 3 t squared minus e to the 2t plus 1 over t. If we want the acceleration, that's the derivative of velocity. Okay, and that might be worth one method mark, just writing a equals v prime. Depends on the mark scheme. Okay, let's differentiate. This is going to give us minus 2 e to the 2t, and this will be minus t to the negative 2. I just think of this as t to the negative 1. Okay, plug it in. We want to find a at 4. So that's going to be 6 times 4 minus 2 times e to the power of 2 times 4, or t to the 8, minus 4 to the negative 2, or 1 over 4 squared. Work that out in your GDC, you'll get negative 5938, okay, or to 3 sig figs, negative 5940. And the units here should be meters per second because it's acceleration. Last thing we're going to look at here, optimization questions. Generally, when you're looking at optimization, you want to draw a clear diagram if at all possible, so they often involve geometric shapes. Construct an equation with the variable to be optimized. And make sure that all your quantities are expressed in terms of this variable. So you don't want to have, say, if you've got cost, you don't want cost equals, I don't know, 2x plus 4y. That's not going to be helpful. Everything needs to be expressed in terms of your x. Find min max using either your GDC, first derivative, and a sign table, or a second derivative test. If it comes up on a paper 2, though, use your GDC to find max and min. So optimization means generally finding a max or a min. Let's take a look at Angie here. She has decided to create a rectangular pen, as so many people in math problems are wont to do. She wants a total area of 30 meters squared. The material required for 3 of the size costs $4 per meter, and the material required for the front costs $9 per meter. Write an equation for the cost of the materials and find the dimension that minimizes cost. Okay, let's see what we know here. I want a rectangle. I want an area of 30 meters squared. I know that these two sides are going to be the same, 30 over x. And then I'm going to have these other sides here, y. No, I'm breaking my own rule here. I've got an x and a y here. Let's see. Can I re-express this length, the y, in terms of x? I know for a rectangle, area equals length times width. Now, I know in this case, area is 30. I decided to call my length y and my width x. So I can re-express the letter y, or my length, as just 30 over x. Oh, that's going to be nicer. Now, you can double check this. Is this really going to give you an area of 30? You betcha. I have no idea what just happened with the smartboard, though. Okay, here we go. If you had area equals x times 30 over x, yeah, that really would give you an area of 30. It'd be pretty unhelpful for us. Now, let's check it out. One of these sides is the front. I'm going to call this the front side. So for our cost is going to be related to perimeter here. It's going to be $4 per meter on that side, on the left side. It's going to be $4 per meter on the back. It's going to be $4 per meter on the right side. And it's going to be $9 per meter on the front. Okay. If this were paper 2, I might collect some terms here and call this, I don't know, 8x. And I might call this 13 of these 30 over x's. But I wouldn't dwell on it too long. I go to the GDC. I put that in. 8x plus 13 over 30, times 30 over x, rather. Okay. A graph. I'm not going to be too disappointed that I'm not seeing this at all. I need to look at costs that are higher than $10. It's going to cost more than $10 for sure to build this. So let's be liberal. Let's say I go up to 500 for our y's. That may still not be enough, but hopefully we'll see some of our graph. Oh, we do see a nice portion of the graph. It looks like it's starting to turn around. Maybe I want to go up to some higher x values just to make sure. So I'll go maybe from 0 to 20 on my x's. There is a minimum to this graph. Let's find it. Go to the left of the min. I should have just put in a number. And then to the right of the min, say 10. And it gives us 6.98. Okay. You might want to sketch your method briefly, just show what you did and that you found a min at 6.98. And it also gives you y value there, 11.71, or 111.71. That's the cost. So the minimum cost that you're going to incur is $111.71. If you make your pen 6.98 by, that gives us our x value over here. We need a different amount for the front and back. So our other dimension is going to be 30 divided by our x value of 6.98, or 4.30. Okay, that gives us our dimensions using our GDC. We've optimized. Now, if you didn't have your GDC, you might say, what am I going to do in this case? Well, for me, I might simplify the original c at x expression a little bit further. Call that 13 times 30 is 390. And that would be over x, so x to the negative 1. If I want a min here, I know that that relates to first derivative. Okay, that'll give me 8 minus 390 x to the negative 2. If I want to find a min, that's going to be a horizontal tangent, so my c prime would be 0. 8 minus 390 over x squared. Okay, I don't like that x squared in the bottom, so I'm just going to multiply both sides by x squared. That's going to give me 0 equals 8x squared minus 390. Equals 8x squared. Divide them up. You get 390 over 8. Hold on, those are both even. Let's simplify or reduce. 195 over 4. Okay, and then we're going to solve by square rooting both sides. It's an equation, so we should consider both positive and negative cases. So positive or negative root 195 over root 4, which is just 2. Only positive one's going to work. Because we're talking about dimensions, we can't have negative dimensions. So that would give us, our dimension on one side is root 195 over 2 by, this will be 30 over root 195 over 2, which if you flip and multiply is 60 over root 195. Now you might say, I'm probably not going to have those kind of measurements on my measuring tape, but those are real values that our measurement could take. I wonder how they compare to our other solutions. The square root of 195 divided by 2. Oh, beautiful. It's 6.98. And then our other one, I hope this works. And I haven't done anything silly. 4.29. Okay, so these are exact solutions that we found analytically. Perfect. The ones we found with our GDC were good enough, and they took us less time. So on a paper 2, obviously, do what's in blue here. Write it at 6.98 by 4.30. If this happened to be paper 1, you're going to have to go the route of finding the exact solutions. Folks, good luck on your final IB exams.